Hello everyone, Shaheen is here. Today I'm going to demonstrate how the second moment of area for a section can be calculated using the tabular method and using Excel. Okay, second moment of area is a very significant geometrical quantity which is related to the flexural stiffness of a section like a beam, and the larger the second moment of area, the stiffer the material, and the larger I, smaller stress induced inside the structure. Okay, so that parameter is designated with the symbol of I in many textbooks. So I is defined as integral of y squared dA. So that is, for example, a rectangle, and this is the neutral axis. This is y direction, and that is how you calculate I. The dimension for that is length to the power of 4. So for some primitive shapes we can find this quantity easily from the table or from the handbook. For example, for a rectangle bending with respect to the ZZ axis, so IZZ, that is 1 over 12 BH cubed, given that this is B, this is the width, and that is H. You find that pre-calculation inside the textbook, but for complex shapes, the problem is complex because either you have to start from first principle to calculate I, or if possible, you can decompose the composite shape into a number of primitive shapes, and there might be several ways of doing that. For example, here I want to solve or calculate the second moment of area for problem 6-85 from Hibbler 5th edition. And the way I propose to decompose is by making one rectangle here plus one triangle minus one circle. So please note how I have laid out these decomposed components. I didn't shift them vertically, simply I have spread them to show that how each decomposed section is located with respect to the centroid of the composite shape. Okay, the first problem is when you are bending a composite shape like that, the neutral axis for that should be calculated, and it's not in the middle or some predictable position. So you need to find out y bar for that cross-sectional area. That is the first thing. Y bar is serving as a reference. So this is exactly neutral plane where the fibers of the bending segment are neither under tension or compression, and on both sides of this axis or plane the fibers are deforming in tension or compression. So one problem with that kind of calculation, even though if you are referring to the table, I can use that I from the table, this one from the table, that one from the table, and combine them. But the problem is the value which I bring from the table, they are calculated assuming they have a different neutral plane. So the neutral plane generally coming from the table are located at the centroid of the decomposed, for example here. And that decomposition has an offset with the centroid of the composite shape. And for each shape, you have to find out that offset and use that offset for calculating the penalty or error to be added to the standard moment of area before you combine them together. So in this diagram, I have tried to demonstrate how this has been conducted. So let me zoom in so perhaps you can see this more clear. So that is the blue hatch section is the cross section of the beam. Y bar is the first thing you want to calculate. And once you have Y bar is compared to the centroid of each decomposed member to find out the offset. So I label these shapes as shape number 1, 2, 3. So the offset for first shape, that is measured from the center of the decomposed shape to the centroid of the composite shape. That is D1. And D2, that is 1/3 of the height measured from the base compared to the centroid of the composite shape. That is D2, the second offset for the second shape. And for the third shape, the centroid of the circle is here, the centroid of the composite there, the distance between them, or the offset, that we show that with letter D3. So there is always a risk of making error when you are trying to calculate this, because you are dealing with some large numbers with decimal places and adding, subtracting. So it's very possible to make an error, and that is why we are using tabular method. Still, tabular method means you make a table, you calculate each individual ingredients of the calculation into these cells before you combine them in a proper way. But the idea is from this table, some calculations are being reused. For example, you will be using AI and Y bar I for finding the centroid of the composite shape, and maybe the same quantities are being used for second moment of area calculation. So that is the advantage of having tabular method. So you put every individual calculation in a proper space. So later on, if you want to check something, you easily come back to it and find where the potential error is, and you fix it. But the reason we want to do this inside the Excel, and I should have told this in front, Excel is a great, not only a calculator, but also a formula spreadsheet. So I know, for example, for calculating Y bar, I need to go with a general expansion of integral into summation. This is Y bar for the first shape multiplied by its area, plus Y bar for the second shape multiplied by its area, minus Y bar for the third multiplied by its area, divided by sum of the positive area, take away the negative area. So these are many individual computations should be done, but Excel makes these things easier if that is used as a calculator and as a formula. So, for example, to show you the idea, I put two numbers here, and the formula here, I start that with an equal sign. That is how you start the formula. And then instead of adding this plus that, I simply type equal, click here, that bring, so let's do that again. So this is equal sign first, and then the number, so let's do that again. So this is some number here, and over there I want to combine these two numbers. The way this can be done is starting with a sign, equal sign, that's the formula. Then instead of keying that number, I click on the cell, that cell would appear here, plus, and I click on the second cell. So now if I approve, that becomes the sum of these two numbers. So whenever I find a mistake, for example, here, and rectify the number, so that sum would be automatically updated. So that is the second advantage of using Excel as a calculator, as a formula book for similar kind of calculation. So let me show you, for example, to calculate y bar, I'm using an annotator. So it's interesting, you can annotate on the same book and do the calculation at the same time. So this cell is where I put the formula. I put this formula here, but look at this. That is, so I have already pre-filled the y bar of each individual segment, 1, 2, 3. I pre-filled their area. So for example, if you are interested to see how the area was calculated, so this is a formula, equal 300 by 200. That means area of segment number 1, which is this rectangle, that is 200 multiplied by 300. And that equal sign is a formula in case if something updates or changes, I can do this. Right, so we start with pre-filling centroid of this decomposed section, and also we fill in the area of the decomposed section. And then these two columns, I'm going to use them for calculating the y bar using a formula. So that to get us started, so look at this. This is equal, and all these colors are being picked from the corresponding cell. So make a comparison between these selected cells and this formula. And yeah, so if I change any of these things as a result of an error or something, my calculated value here would be updated. So that, according to this calculation, I find y bar equal to 132.67647. The next thing I want to calculate is di. This is the offset between each individual decomposed shape and that of the composite shape. So that is even easier by noting, for example, I want to find d1. d1 is the difference between M2, which is centroid, minus M7. M7 is the centroid. So the difference between centroid of the shape and centroid of the total shape, that is offset for the first shape. Okay, so that is automatically calculated. For example, for the second shape, the offset is the difference between centroid of the second shape and the centroid of the composite shape. And likewise, we do the same thing for the third one. So that is clear. Next, I want to recycle some of the values here. I want to make that offset squared multiplied by its area. So all I have to do is, at this cell, I put a formula that is equal the cell sitting as di squared multiplied by the cell which is sitting as ai. And because of that equal sign, a formula, when I click, that would find out the thing. And interestingly, if I drag this handle down, the very same formula will be repeated for the following rows. So this row would look at the left values for calculation. This row would look at the left side for the calculation. So easily, we managed to calculate the penalty for each decomposed shape. Now, the next step is I would enter, or I would key in the standard value of each decomposed shape. For rectangle, that is 1/12 BH3. So that is equal to 1/12 B multiplied by H3. For the first rectangle, B, which is the width, is equal to 200. Height is 300. So that is the standard value of I. So for triangle, the formula from the standard book is 1/36 BH cubed. So we enter that. For circle, the standard I is pi multiplied by radius to the power of. Okay, that should be 4. I made a mistake here, so let me rectify this. The radius to the power of 4 divided by 4. Okay, so that makes this one corrected. This is pi r4 divided by 4. This is the second moment of area for the rectangle. Now, to find out the total moment of area, I need to combine the value of the I, but each I is composed of the standard plus the penalty. So that is, I'm adding all the standard values together here, and the last term is being subtracted because this is a cavity, this is a hole inside the material. So instead of adding that to the previous one, I have subtracted it. So this cell, that is summation of all the standard values, and in this cell I put another formula, which is sum of the penalties for the first, second decomposed shape, take away the penalty for the whole. And now all I have to do is to calculate the I need to add these two numbers together. In this case, I make a formula and add this plus that, and this is being calculated here. So you see that once you learn this technique, it is quite handy, and it lets you to find out the second moment of area, or for similar calculation you can use this. And I'm going to save this Excel file and share this together with this video. So in case if you want to follow this step by step, you can use a combination of the video and the file together. I hope you find this useful, and looking forward to talking to you soon. And that is all I have for today. Take care. See you soon. Bye.